Dry cleaning processes in semiconductor industry. Dry cleaning processes in the semiconductor industry are essential for removing contaminants from wafer surfaces without using liquid chemicals. These processes are especially useful in advanced node technologies, where precision and material compatibility are critical. There are three major categories: plasma cleaning, vapor phase cleaning, and CO2-based cleaning. Plasma cleaning involves high-energy plasmas that react with and remove organic residues, native oxides, and particles from surfaces through ion bombardment and reactive species. Vapor phase cleaning utilizes gas phase chemical reactions to etch or remove specific contaminants without the need for rinsing or drying steps, reducing water usage and minimizing stiction risks. CO2 cleaning uses either cryogenic or supercritical carbon dioxide to lift away particles and residues gently, making it suitable for fragile structures. Together, these dry cleaning techniques support high yield, process integration, and cleaner semiconductor manufacturing environments. Introduction to semiconductor cleaning. Semiconductor cleaning is a foundational process that ensures wafer surfaces are free from contaminants before moving to the next step in the manufacturing process. Cleaning plays a critical role in three key areas. First, it removes unwanted particles, residues, and films from the wafer surface. Second, it prepares the wafer for subsequent steps, like deposition or etching, where surface quality directly affects performance. And third, it helps maintain high product quality and long-term device reliability. Contaminants can include dust and debris, which are physical particles, as well as organics like photoresist residues and oils. Metallic ions such as iron, copper, sodium, and potassium can also cause electrical interference. Finally, native oxides must be removed or controlled. Cleaning is critical because semiconductor devices demand extremely high purity, often 99.9%, and precision at sub-10 nanometer feature sizes, leaving no room for contamination. Introduction to semiconductor cleaning. Impact. Cleaning has a profound impact on the performance and efficiency of semiconductor manufacturing. First, it directly contributes to yield improvement. By effectively removing contaminants from the wafer surface, fewer defects occur during subsequent processing steps. This can lead to an increase in yield by as much as 15%, meaning more functional chips are produced per wafer. Second, effective cleaning drastically reduces defects by as much as 80%. These defects could otherwise lead to device failures, impacting both performance and cost. Finally, thorough and precise cleaning improves overall reliability by up to 25%. This means devices not only function as intended, but also remain stable and durable over time in real-world applications. In summary, semiconductor cleaning is not just a supportive process. It is a driving force behind yield enhancement, defect elimination, and reliability improvement, forming the bedrock of successful semiconductor manufacturing. Cleaning methods. Overview: wet versus dry cleaning. Semiconductor cleaning can be categorized into two primary methods: wet cleaning and dry cleaning, each with distinct approaches and advantages. Wet cleaning uses chemical solutions, with methods including RCA cleaning, which involves SC1 and SC2 solutions, Piranha solution for organic removal, HF etching to eliminate oxides, and ultrasonic cleaning for physical dislodging of particles. These techniques rely on liquid phase reactions and tend to generate chemical waste. On the other hand, dry cleaning involves gas phase processes like plasma cleaning, CO2-based cleaning, vapor phase reactions, and cryogenic methods. These techniques use gases or plasma to clean surfaces, often with minimal waste. Key differences include the medium used, liquids versus gases or plasma. Wet cleaning is more chemical and bulk-oriented, while dry cleaning offers cleaner, more precise results. Dry methods are particularly useful for advanced nodes, where minimal damage and contamination control are critical to achieving nanoscale precision. Cleaning methods. Overview: advantages and challenges. Both wet and dry cleaning methods offer distinct advantages and face specific challenges in semiconductor manufacturing. Wet cleaning excels at removing contaminants efficiently. It uses well-established chemical processes like RCA and HF treatments, making it cost-effective and highly selective for specific materials. However, it also poses several challenges. Managing chemical waste is costly and environmentally sensitive, and the high water usage raises sustainability concerns. Wet cleaning can also damage delicate surfaces and requires additional steps for drying wafers, which adds time and complexity. Dry cleaning, in contrast, generates no chemical waste, offering a cleaner and more environmentally friendly option. It provides precise control over cleaning parameters and eliminates the need for drying. However, these benefits come at a cost, literally. Dry cleaning systems are more expensive and involve complex control systems. They also offer limited material selectivity and can be difficult to optimize for every wafer type. That's why many fabs today use a hybrid cleaning approach to balance performance, cost, and environmental impact. Plasma cleaning process. Plasma cleaning uses ionized gas technology to remove contaminants from surfaces with high precision. It begins with gas ionization, where RF energy energizes process gases, converting them into plasma, a state rich in reactive ions. These high-energy ions bombard the wafer surface, effectively dislodging unwanted particles. The process continues with chemical reactions, where contaminants interact with reactive species in the plasma, forming volatile compounds. Finally, these reaction products are evacuated using a vacuum system, leaving behind a clean, dry surface. There are several plasma types for various applications. Oxygen plasma targets organic residues, argon plasma delivers physical cleaning, hydrogen plasma supports reduction reactions, and CF4 plasma is used for etching. Key benefits include being environmentally clean with no chemical waste, precise control over material removal, and a fast process with short cycle times. Additionally, there's no drying required, eliminating watermarking, and it operates at low temperatures, minimizing thermal stress on materials. Plasma cleaning process, applications, parameters, and considerations. Plasma cleaning supports a range of precision applications in semiconductor manufacturing. It is used for photoresist stripping, removing residual mask materials after lithography. Surface activation improves adhesion by modifying surface chemistry. Polymer removal is critical for clearing residues left from etch or deposition steps. Additionally, oxide etching allows controlled removal of oxide layers without damaging underlying structures. To enable this, several key parameters must be controlled. RF power typically ranges from 100 to 1000 watts. Operating pressure is kept between 1 and 100 millitorr. Temperature can vary widely from 20 to 200 degrees Celsius. Process times are relatively short, typically between 30 seconds and 5 minutes. Various equipment types are used, including RIE systems, ICP reactors, and microwave plasma tools. However, some considerations must be addressed. Selectivity can be an issue. Improper tuning may damage underlying materials. Uniformity challenges may arise due to edge effects and loading. There's also high initial equipment cost, and process complexity requires optimization across multiple variables. Plasma cleaning process, market impact, and industry value. Plasma cleaning has become a foundational process in semiconductor manufacturing due to its unmatched precision, performance, and environmental advantages. Today, an impressive 75% of fabrication facilities, fabs, rely on plasma-based techniques for cleaning and material removal. This widespread adoption reflects the industry's trust in plasma's effectiveness for applications such as photoresist stripping, polymer removal, and surface preparation. From an economic perspective, the market size for plasma cleaning technology stands at $2.1 billion, underscoring its strategic importance across global supply chains. With advanced capabilities that support high throughput, environmentally friendly, and selective processing, plasma systems offer a high return on investment for fabs aiming to meet both yield and sustainability goals. Ultimately, plasma technology embodies the formula: plasma equals precision, performance, and sustainability, making it an essential component of modern semiconductor manufacturing, from cutting-edge nodes to legacy device production. Carbon dioxide cleaning processes. Carbon dioxide cleaning is a powerful alternative to traditional wet or chemical-based methods. So, why choose carbon dioxide? First, it's eco-friendly. Carbon dioxide is non-toxic, safe, and doesn't contribute to chemical pollution. It leaves zero residue, ensuring a truly clean surface without introducing contaminants. Additionally, it's cost-effective, offering an efficient and streamlined solution for sensitive components. At its critical temperature of 31.1 degrees Celsius, carbon dioxide exhibits unique dual-phase properties, combining the gas-like density for penetration into microcavities with liquid-like solvency for dissolving contaminants. These properties allow carbon dioxide to flow easily into small features, with no surface tension and tunable solvent power, making it highly effective for precision cleaning. Carbon dioxide in its dry ice form, at -78.5 degrees Celsius, utilizes several powerful cleaning mechanisms. These include kinetic impact, thermal shock, and sublimation. These mechanisms enable aggressive cleaning, while still producing no residue and delivering a fast process. Altogether, CO2 cleaning offers a balance of safety, precision, and performance. CO2 cleaning processes, applications, and method comparison. CO2 cleaning plays a critical role in modern semiconductor fabrication. Its key applications include photoresist removal, where it effectively strips mask layers after lithography without introducing new contaminants. It also excels at particle cleaning, dislodging and eliminating microscopic debris from wafer surfaces. CO2 is ideal for tackling post-etch residues, which are chemically resistant and difficult to clean using traditional methods. Additionally, it supports wafer drying, leaving no watermark or residue. There are two main CO2 cleaning methods: supercritical and cryogenic. The supercritical method uses CO2 above its critical temperature and pressure, providing gentle and precise cleaning. It penetrates microcavities and dissolves contaminants without mechanical stress. The cryogenic method, on the other hand, uses dry ice particles for fast and aggressive removal through impact and thermal shock. Altogether, CO2 cleaning is summarized by its value proposition: CO2 equals clean, green, and efficient, offering a sustainable, residue-free, and effective solution for delicate semiconductor surfaces. Vapor phase cleaning. Vapor phase cleaning involves the use of reactive gases to chemically remove contaminants from semiconductor surfaces without liquid immersion. Several key gases are utilized in this process, each selected based on the temperature and materials involved. Nitrogen trifluoride, or NF3, operates effectively at high temperatures between 300 and 500 degrees Celsius and is widely used in chamber cleaning due to its strong fluorine-based reactivity. Another high-temperature cleaning gas is chlorine trifluoride, which functions at 150 to 300 degrees Celsius and is known for its aggressive cleaning action. Xenon difluoride is unique in that it works at room temperature, making it ideal for selective etching applications, particularly for sacrificial silicon layers. Hydrogen fluoride, or HF, functions in a lower temperature range of 20 to 100 degrees Celsius and is used for removing native oxides. Lastly, ozone, O3, is used between 80 and 200 degrees Celsius for oxidizing and stripping organic residues. Applications and safety in vapor phase cleaning. Vapor phase cleaning technologies serve several critical functions in semiconductor manufacturing. One major application is chamber cleaning, especially in CVD systems, where reactive gases remove deposition buildup and maintain process consistency. Another key use is resist strip, which involves post-etch cleaning of photoresist residues using gases that react with carbon-based films. Vapor phase cleaning is also integral in silicon etching, particularly for MEMS release, where precision and selectivity are essential. Additionally, oxide removal is common for surface preparation before critical process steps, such as thin film deposition. However, these processes come with significant safety risks. Gases like HF are extremely corrosive, posing hazards to both personnel and equipment. ClF3 is highly reactive, increasing the risk of unintended reactions. NF3 has a high global warming potential, raising environmental concerns. As a result, strict safety requirements must be met. These include emergency protocols, leak detection systems, gas abatement infrastructure, and comprehensive personnel training programs. Process control and equipment in vapor phase cleaning. Successful vapor phase cleaning relies on precise process control and specialized equipment. Temperature control spans from room temperature up to 500 degrees Celsius, depending on the chemistry and target material. Pressure control is equally critical, with operational ranges between 1 millitorr and 1 atmosphere. These ranges accommodate different gas phase reactions and allow engineers to fine-tune reactivity and selectivity. Mass flow controllers ensure the accurate delivery of gases, while thermal activation methods enable the decomposition or activation of reactive species. Gas dilution is used to moderate reactivity and enhance process uniformity. On the equipment side, furnace systems operate in a wide temperature range from 200 to 1000 degrees Celsius, supporting high-temperature cleaning and etching processes. Rapid thermal processing, or RTP systems, enable fast ramp-up and cool-down for time-sensitive applications. Gas cabinets are essential for the safe storage of toxic and reactive gases. Finally, abatement systems are required to capture and neutralize exhaust gases with over 99% efficiency, ensuring environmental and personnel safety. Advantages of dry cleaning. Dry cleaning in semiconductor manufacturing offers several distinct advantages over traditional wet cleaning methods. Environmentally, it eliminates the need for liquid waste disposal, reducing chemical use and completely avoiding water consumption. This helps conserve natural resources. Recyclable gases in closed-loop systems and lower emissions also contribute to a reduced carbon footprint, aligning with sustainability goals. From an efficiency standpoint, dry cleaning is 50% faster, with process times ranging from just 5 to 15 minutes compared to 30 to 60 minutes for wet cleaning. There's no need for drying time, which enables immediate transition to the next processing step. It also supports batch processing for multiple wafers and offers precise temperature control for consistent outcomes. In terms of quality, dry cleaning delivers 10 times better uniformity, with minimal surface damage, excellent selectivity, and essentially zero residue. It provides nanoscale and molecular level removal, with selective targeting and gentle processing. Economically, dry cleaning reduces operating costs by up to 40% through chemical savings, elimination of waste disposal needs, and reduced water treatment and maintenance requirements. Expanded benefits of dry cleaning. Dry cleaning offers numerous safety advantages compared to traditional wet processes. It involves non-flammable chemical reactions, reducing the risk of fire. Operators face lower chemical exposure due to minimized liquid handling, and automation further reduces human intervention, enhancing workplace safety and minimizing handling risks. In terms of throughput, dry cleaning excels by processing over 200 wafers per hour. With an impressive 98% system uptime and a yield rate of 99.5%, it supports consistent, high-volume manufacturing with minimal downtime or defects. Compatibility is another strength. Dry cleaning is effective on silicon wafers, compound semiconductors, MEMS devices, and delicate structures, making it versatile across diverse applications. From an investment perspective, dry cleaning systems offer a strong return on investment. The typical payback period is only 18 months, with potential annual savings exceeding $500,000. Efficiency improves by 35%, and yield can increase by 2 to 5%. Importantly, dry cleaning is future-ready. It supports advanced technology nodes, scales easily, integrates with IoT systems, and aligns with green manufacturing goals. Challenges and limitations. Implementation barriers and solutions. The implementation of advanced semiconductor processes often encounters several technical and process-related barriers. One major technical barrier is equipment complexity. Modern systems require sophisticated control mechanisms to manage multiple variables with high accuracy, increasing the cost and training demands. Another concern is gas handling safety. Many processes involve toxic or hazardous gases, which necessitate strict safety protocols and monitoring to protect personnel and the environment. Furthermore, process control is a critical challenge. Achieving consistent outcomes requires precise monitoring and adjustment of process parameters such as temperature, pressure, and timing to maintain yield and performance. On the process side, there are clear limits. One is limited material compatibility. For instance, organic materials can suffer thermal damage, while metals may oxidize under certain conditions, limiting the flexibility of some processes. Lastly, selectivity issues remain a hurdle. Precisely targeting one material without affecting others is difficult, often requiring sophisticated solutions and trade-offs. Economic impact. Implementing advanced semiconductor processing systems requires a significant upfront investment, ranging from $2 million to $5 million. The equipment alone can cost between $1 million and $3 million, depending on the configuration and capabilities. Infrastructure needs, such as cleanroom integration, gas delivery lines, and safety enclosures, add another $500,000 to $1 million. On top of that, training for engineers, operators, and technicians can cost between $200,000 and $500,000 due to the complexity of the systems and the safety considerations involved. Ongoing operational costs also add to the economic burden. High-purity gases are essential for precise processing, but come at a premium. Specialized maintenance is required regularly to ensure safety and performance. Labor costs are higher as well, since only skilled operators can handle these systems. Additionally, abatement systems must be installed and maintained to safely manage hazardous byproducts and comply with environmental regulations. Safety risks. Safety is a major concern in semiconductor processing environments due to the presence of toxic gases and extreme operating conditions. Toxic gas exposure represents a high-risk category, especially with substances like hydrogen fluoride, HF, which can cause severe chemical burns upon contact. Handling HF requires strict protective protocols and continuous monitoring. High-temperature operations introduce burn hazards. Equipment surfaces and processed materials can reach temperatures capable of causing instant injury. Pressure systems also carry the potential for explosions if not properly managed, necessitating pressure relief systems and routine checks. In emergency situations, the protocols are complex and must be well rehearsed, as time is critical in mitigating hazards. Facilities must invest in emergency response training and infrastructure. Together, these risks underline the critical importance of robust safety measures and regulatory compliance in process design and daily operations. Skills gap. A significant barrier to implementation in semiconductor processing is the widespread skills shortage, estimated at 65%. This shortage is most acute in two critical areas: process engineers and safety specialists. Process engineers are in high demand due to the complexity and precision required in system operation and optimization. Safety specialists are also critically needed to manage risks related to toxic gases, high temperatures, and emergency protocols. To address these shortages, rigorous training requirements are essential. Most roles require 6 to 12 months of specialized training before individuals can operate or oversee systems independently. Mandatory safety certifications ensure that employees are fully aware of hazards and proper mitigation strategies. Continuous education is needed to stay updated on evolving technologies and standards. Emergency response training is also crucial, preparing staff to handle critical incidents with confidence and speed. Solutions. Despite the many challenges, several solutions are emerging that can address both technical and workforce barriers. On the technology front, AI-powered control systems are helping streamline operations, minimize human error, and optimize performance in real time. Enhanced safety systems reduce exposure risks and automate emergency responses. Tailored training programs are also being developed to quickly upskill workers in both engineering and safety domains. Industry partnerships play a vital role in creating shared standards and training pipelines. From a financial perspective, these solutions offer a favorable return on investment. With effective implementation, the typical break-even timeline is just 2 to 3 years. While initial barriers may seem steep, they represent opportunities to innovate, modernize infrastructure, and build a more skilled workforce. In this way, challenges can ultimately fuel progress and long-term competitiveness. Conclusions and future trends. Strategic path forward. Looking ahead, the adoption of advanced process technologies in semiconductor manufacturing promises substantial benefits. One of the most impactful improvements is a 50% increase in processing speed. Faster processing allows for greater throughput, helping fabs meet rising global demand without needing to expand floor space. Alongside this, there's a 40% cost reduction, made possible through process optimization, AI-driven efficiency, and reduced waste. These gains translate into stronger profitability and more competitive manufacturing operations. Equally compelling are the quality and sustainability benefits. With proper implementation, yield rates can reach as high as 99.5%, meaning fewer defects and higher output per wafer. This dramatically reduces rework and scrap. Environmentally, the push towards zero waste is gaining momentum. Waste-minimizing processes, safer chemistries, and improved abatement systems support sustainable manufacturing. In summary, embracing these future trends leads to faster, cheaper, cleaner, and more reliable semiconductor production. The industry stands at a pivotal point where innovation meets impact. Conclusions and future trends. Market growth. The semiconductor processing market is on a fast track to expansion, with annual growth projected at 15%. By 2030, the global market size is expected to reach an impressive $12.5 billion, reflecting the increasing demand for high-performance chips in applications like AI, automotive electronics, 5G, and beyond. This growth is driven by innovations in processing techniques, improved material utilization, and demand for advanced nodes. Another compelling trend is the widespread adoption of these technologies across the industry. By 2027, approximately 85% of manufacturers are expected to have adopted next-generation processing methods, particularly those that integrate automation and AI. This shift is not just about speed or scale, it's about intelligence. AI integration enables next-gen control systems that optimize process variables in real time, reduce human error, and enhance yield. As these technologies become standard, the industry will become more efficient, adaptive, and sustainable, setting the stage for long-term global competitiveness.